Hi, everyone. Thanks for coming for this special Monday high energy seminar. We have today Sanskriti visiting us today. She's a NASA Hubble Fellow at Stanford University, and previously she was a KIPAC postdoctoral fellow at the Copley Institute for Particle Astrophysics and Cosmology at Stanford. She did her PhD from the Department of Astronomy at the Ohio State University, and she works on various observational aspects of the circumgalactic medium of spiral galaxies. And today we will talk about where the hot universe meets the energetic universe. Take it away. Thanks for being here.
Thank you. Also, thanks for putting a lot of effort to pronounce my name right. Hello, everyone. I'm Sanskriti, as he said. I'm an NASA Hubble Fellow, and I'm generally interested in observing different phases of the circumgalactic medium across the wavelengths from radio to X-ray. And today I'm going to talk about the hottest end observed with X-rays. So I'll start with the basic introduction of what circumgalactic medium means, because often, I don't know why the slides are not advancing. Anyway, sorry. So circumgalactic medium simply means anything that's outside the interstellar medium of a galaxy and extended out to the virial radius. Obviously, the hot gas doesn't stop existing abruptly at the boundary of the virial radius. So roughly speaking, anything outside, say, 30 kiloparsec for a Milky Way-like galaxy and extended out to 250 to 300 kiloparsec, that's the extent of the circumgalactic medium. Now, if you think of a Milky Way-like galaxy, the main properties of the CGM is going to be controlled by the virial properties. So if the gas is in hydrostatic equilibrium, we expect the gas to be roughly in million Kelvin, which is observable in principle in X-ray. Now, why do we even care about the CGM, given that we understand the star-forming part, the disk of galaxies, so well? Well, broadly speaking, there are a couple of things that we can try to understand. One is the missing galactic variance problem, and often it is confused with the missing variance problem. So on an average scale, we know that there is a lot of gas in the cosmic wave. So the question is not about how much gas is there in the CGM compared to the cosmic wave. The question is, do all galaxies retain all of their budgeted variance inside the CGM or not? How does it change with different galactic properties? Does it really depend on the feedback or accretion histories, etc.? And even if it retains all the gas, what is the phase distribution? Is it always the hot phase or something else? We really do not know, because all the phases of CGM are not well observed, and especially in the hotter phase, because of the intrinsic difficulty of observing in X-rays, the hot CGM is very poorly constrained. So until we observe the hot CGM well, we do not really know the phase distribution. The related problem is missing metals and missing feedback problem. And often it is assumed that finding all the missing variants is also meaning finding all the missing metals. But the problem is finding all the missing variants doesn't really mean we have found all the missing metals. It could just be a lot of unprocessed variants that's just ionized by the metagalactic background. We do not really understand the accretion history in the large scale well. So if we find a lot of variants outside the galaxy, it is totally possible that it was not accreted in the first place. On the other hand, metals are an unambiguous stressor of the feedback. It has to be processed inside stars. It has to come from the stars to the ISM, to the halo, and also outside. So once we can trace the metals, we know that it has indeed come from the galactic feedback, be it a stellar origin feedback. And that naturally brings us to the missing feedback problem. Because when the outflows are coming, it is not only carrying a lot of metals, it's also carrying a lot of energy and momentum. And we need to take into account of where all of these energies are going. Is it staying in the ISM or the CGM? Is it leaving the galaxy forever? Is it getting recycled back to the ISM? What is happening and how it is changing with different galactic properties? Now, as you might already know, there is a lot of observations in UV and optical probing the intermediate phases of the CGM. And that is simply because it is much easier to observe them in UV and optical. One, because there are amazing instruments like HSG and COS. And also because the oscillation strength of the metal tracers are significantly higher in UV and optical, and often it's an order of magnitude lower in X-ray. So even if you have equal quality of telescopes, it will be significantly harder to detect things in X-ray, simply simply because the tracer elements, despite being present in a larger amount, their oscillation states are much smaller. So it is very harder to detect them in X-ray. So the fact that we do not know about hot CGM is not because they're not there. They could be there and they could be the most massive components. It is just because of the observing difficulty we haven't learned that much about the hot CGM. And what we have learned mostly about is the intermediate or the cooler phases. And because of a lot of ionization uncertainty in those calculations, you can have more than a factor of 50 uncertainty in the calculated mass in the intermediate phases. So in this talk, I'm going to focus mostly on the hot CGM of Milky Way as well as external individual galaxies. And as you will see, in case of Milky Way, we have now moved fast from detection to characterization, while in case of external galaxies, we are still at the phase of detection, although to like limited number of targets. So I will start with the Milky Way because one, it is always going to be the best observed galaxy, just like Sun is the best observed star, but also because the CGM of Milky Way is an omnipresent foreground for all external galaxies. So even if you don't care about the Milky Way, you have to care about the Milky Way if you're an observer, because modeling the contribution of Milky Way and separating that is the main challenge while detecting the external galaxy CGM. And if we start from the X-ray emission, which is the most traditional way of looking for the hot CGM, the prediction actually gets back to 1956, but it took 40 years to detect that in Rosette and separate it from the local hot bubble, which is even much stronger and the unabsorbed component within which we are literally sitting. And Rosette was the first telescope that could separate the absorbed emission from the CGM, from the local hot bubble. It was not called CGM back then. It was called transabsorption emission, which is any emission that's passing through the absorption of the galactic disk. And then after Rosette, all the CCDs from Chandra, Suzaku, XMM, Halosat, Rosetta, everything that has followed, that has allowed us to do spectroscopic analysis to separate the temperature and the density. Now, I'm not going to talk about all the details and the maze happening in the soft X-ray, but primarily you can see two bumps coming from oxygen 7 and 8, helium-like and hydrogen-like emissions from oxygen gas. The line ratios gives you the temperature and the underlying continuum gives you the constant on emission measure or the density square. So roughly speaking, it is a line emission dominated regime where 90% of the emission comes from the lines and barely 10% comes from the emission measure. And that is why we always have a better constant on the temperature than the density. Now, roughly speaking, there was a pretty nice consensus across all the observations in the first 20-25 years. One, the temperature measured across the sky is practically constant and also consistent with the real temperature of the Milky Way, which is too good to be true. But the emission measure varies by an order of magnitude across the sky without any proper correlation with the galactic coordinates. So at a zeroth level, we often model these with an ellipsoid just because as humans we love symmetry. But in reality, it is more like a cosmic amoeba which has, very oddly high emission measured in certain random directions. And similarly, just like X-ray emission, we can also observe exactly these same two oxygen 7 and 8 emissions in absorption as well, targeting toward X-ray bright quasars. And thanks to the gratings of Chandra and XMM Newton, in the last 20 years, it has also been possible to constrain the absorption from oxygen 7 and 8. And from the column density ratios, here again, we can calculate the absorption temperature. And here again, people had an amazing consensus in the first 20 years. The temperature from absorption is consistent with emission. That means we are seeing the same hot gas, and also it's roughly constant across the sky. Column density again varies by an order of magnitude across the sky without any correlation with galactic coordinates. Again, you can start with a sphere and then you can see that it is again a different type of cosmic amoeba. And the absorption emission doesn't really have any correlation. That means the direction with high column density doesn't necessarily have high emission measure. But as emission and absorption have different dependence on density, one can combine them to break the degeneracy between path length and density and hence calculate the mass. And that tells you that the mass of the hot CGM, only if you combine emission and absorption, gives you a really large mass of the Milky Way, closing the galactic balance census for a reasonable assumption of the metallicity. And the emission only accounts for a very small fraction of the gas. showing you that the density squared measured mass accounts for a very small fraction of the mass, implying if you focus just on emission or just on absorption, you are going to under or overestimate the mass. You have to combine them together. Now, after this, it might look like a self-destructive talk, because till now it looks like everything is pretty much consistent. Temperature is, consistent with the virial temperature across the sky. Also, the mass makes sense. It is pretty much what you expect. But as you might have already realized, all of these assumptions are based on oxygen 7 and 8. And the underlying assumption is that we are assuming all of oxygen 7 and all of oxygen 8 are coming from a single phase. We haven't verified that yet. And also when we calculate the total mass, we assume that oxygen to other metal abundance ratios are perfectly in solar chemical composition. At the zeroth level, it is a fair assumption, but if we have an option to verify that, we should. So now that we have detected the gas both in emission and absorption, I will try to address all of these questions one by one and start with these two. Is the chemical composition really solar? And also, do we have anything else apart from the virial gas in X-ray? One of the simplest way to do this is simply going beyond oxygen and trying to probe other metals like carbon, nitrogen, neon, magnesium, whatever transitions you have in X-ray. While the principle sounds very simple, detecting those are really challenging because one, they are much less abundant than oxygen, so your data has to be of very high quality. And secondly, now we are fitting a very large range of wavelength. We have to fit from 4 to 45 angstrom, and that means the continuum fitting becomes really painful. You have to fit the continuum of the AGN, you have to fit the local continuum, and also what we call the pseudo continuum coming from a lot of line absorption from the cooler phases of the Milky Way. So in X-ray, the inertial transitions of even the cooler phases come, and that adds a lot of pseudo continuum in X-ray. That makes it really challenging to fit all the lines together, but we have been able to do in a couple of sightlines, and I'm going to show the example of just one sightline. This is toward Markarian 421, so this has the highest signal to noise in the whole archive of breaking. For obvious reasons, it's the brightest X-ray laser in the sky. And simply after going beyond oxygen, we start seeing a lot of lines, as you can see here. But detecting the lines is not just the interesting thing. One, we detect a lot of interesting, already known lines at an unexpected string. For example, we have carbon 5 and nitrogen 7 and magnesium 11 at an unexpected string. And secondly, we have a lot of lines we didn't expect to detect in the first place, like neon 10, magnesium 12, sulfur 16, silicon 14. These are very extreme lines that you do not expect in a million Kelvin gas in any normal physical scenario. So if we have to explain all of these lines together, a hybrid ionization model reveals that in addition to the virial phase, which you obviously expect here, there is a supervirial phase that's an order of magnitude hotter and has a significant column density. And it is only probed only when you have these extreme lines. And in addition, we have a subvirial phase, which is often often probed with UV with a lot of ionization assumptions. But here, since we have multiple ions and we have more stable ions like helium light, we have a much better constant on temperature and column density as well. So toward the same single sightline, we can find 3 different phases with very well constant temperature and column density. And the moment you have more than one metal, you can get abundance ratios as a bonus. And here we have some examples again toward one sightline because it's a complete maze when you start looking at all the sightlines. Here, the dashed line, the solid line shows you the solar composition. And as you can see, the best fits are significantly supersolar. So what we find is that different alpha element ratios are different across phases toward the same sightline. And for the same phase, it is also different across different sightlines. So the chemical abundance ratio is extremely inhomogeneous across phases and across sightlines. And also what we were not looking for is that we didn't detect any iron. But in the model, since we started with solar-like chemical composition, the model predicts a lot of strong iron lines that we do not detect, which means iron has to be subsolar, or a different way of saying is that it is alpha enhanced. So alpha to iron ratio has to be significantly supersolar to explain the non-detection of iron lines. Now, none of these, the existence of supervirial gas, the existence of supersolar alpha to iron, and the existence of this inhomogeneous chemical abundance, these were not predicted in theories. This tells us that we do not really understand how the metal loading and metal mixing happens in the CGM, simply because we didn't look at these extreme phases earlier. And we also looked for this gas in emission, because if you are seeing it in absorption, why not see it in emission? And same as before, oxygen 7 and oxygen 8, just like it doesn't come from the same phase in absorption, it also doesn't come from the same phase in emission, but you need a really deep data to separate them out. This is actually, I think, a 1.8 megasecond of data. So you don't really get that very often in the archive at least. So we detected this first with XMM, and then it was followed up with 3 different instruments, Suzaku, Helosat, and eROSITA. And now we have a new consensus. So the virial phase is obviously there as it is, but there is a supervirial phase in emission in 60% of the sky, not everywhere, but 60% is also significant. And it is consistently an order of magnitude fainter than the virial phase, which is why it was hard to detect earlier. But it's there in 60% of the sky. And also, unlike the virial phase, which has practically a constant temperature, its temperature often varies across the sky. It can be sometimes more than an order of magnitude hotter, sometimes a factor of a few. Now, same as the absorption, where we see such, supersolar alpha to iron and non-solar abundance ratios, we try to see what is dominating the emission here. Now, depending on the exact temperature, it could be oxygen, it could be neon or magnesium, because the temperature is varying. But overall, we see that often it is dominated by the iron emission. And also, if we force the iron abundance to be smaller, we cannot feed the emission. So there has to be obviously unambiguously iron emission that is dominating the emission from the supervirial. Now, if you remember from just 2 slides back, we did not detect any iron in absorption. And in emission, it is dominated by iron. So iron cannot be present and absent in the same time, in the same phase. We often talk about the differences in emission and absorption in terms of density bias. But in addition to density and temperature bias, because of these chemical abundances, we can unambiguously say there has to be 2 distinct supervirial phases. Despite being different, having similar temperature, they have to be two different phases because of their different chemical abundances. And since we simply know that iron comes from different stellar feedback, like iron comes from a different type of supernova, and the alpha enhancement comes from different supernova. The rough inference is that the supervirial gas in emission and absorption has to have different stellar feedback origins. Now I will quickly run through the other 3 aspects. One is the non-thermal sources. Do they contribute at all? Now, if we compare the total broadening and the thermal broadening of oxygen lines, if you do not have any non-thermal broadening, all of the data points will lie on this green line. And as you can clearly see, most of the data points are above. So the total broadening is significantly above the thermal broadening, implying that the total broadening is actually dominated by non-thermal broadening. Now, in cooler phases, it is already known that the non-thermal broadening dominates. But in hotter phases, the thermal broadening already is getting larger simply because of the temperature. But even here, we can see there is significant contribution from non-thermal sources. And next, we can also try to constrain the line of sight velocity, although with the existing rating, we do not have great constraint. But currently, we have some very rough trend of what is happening across phases. So if you focus just on oxygen, we often see that there is practically no velocity. So the virial phase is practically quasi-static. But often in subvirial phases, we see that the gas is inflowing, and in supervirial phases, we see the gas is outflowing, although sometimes we see inflowing gas as well. Now, currently, we do not have good constraint to really say what the velocities are. But if these trends are true, we might have better constraint about the outflow history in addition to what we see in UV. And lastly, what I have been talking about is the CGM, but it is Milky Way CGM, and we are sitting in the ISM. So the question is, what fraction of this observation is truly in the CGM, and what fraction of the ISM is contaminating? So we test that in 2 different ways for emission and absorption. So in the left, you can see we are doing it in emission, where we target molecular clouds at high galactic latitude. Thanks to its very high column density, it blocks all the non-local emission, while here in the blank sky, we can observe the CGM and ISM together. So if the supervirial phase is truly coming from the CGM, we will see this excess only in this sideline. And here, as you can see, the supervirial phase is obviously coming only from the blank sky directions. And similarly, we do the test in absorption as well. Here we take the X-ray binaries with well-measured distances in our galaxy. Here again, we are measuring only the ISM absorption, while to the AGS, we are measuring the ISM and CGM together. Here again, you can see we do not detect any ISM absorption, while we detect a lot of neon-10, silicon-14, and sulfur-16 toward the ISM plus CGM directions. So in both cases, we can see the excess emission and absorptions are coming primarily from the CGM. Now, lastly, while I have been talking about the Milky Way, we should also talk about the external galaxies a little bit, although it has been really challenging to detect the CGM of hot external galaxies, simply because more than 90% of the emission comes from the Milky Way itself. And that is why we need to understand the Milky Way in great detail. So this is actually the single galaxy in extra emission, where we have the detection from the integrated region from 30 to 200 kiloparsec. And just to emphasize on how challenging this detection is, so these gray points are the total emission. And this, if you are following the laser point, this dashed curve is the total soft X-ray background. And this tiny excess coming from oxygen 7 and iron 17, that is coming from the CGM of an external galaxy. It barely contributes to, I think, 7% of the total photon counts in soft X-ray, implying that the systematics have to be, calculating the systematics have to be the main challenge. And right now we just have one galaxy simply because we have been applying for time for last probably 7 cycles and we haven't been awarded that yet. But yeah, we are hopeful. And we have also tested this in 3 different ways. I'm keeping this for now, but if anyone is interested, I can talk about how we test that it is truly extended. The fact that you find something between 30 to 200 kiloparsec doesn't mean it is extended. It could just be very close to 30 kiloparsec. So we test that in 2 different ways and also test that whether it is some random fluctuation in the Milky Way or it is truly radially correlated with the target galaxy. And lastly, we also try to look for the hot CGM of external galaxies in X-ray absorption. So here we take the help from UV. In UV, we have the oxygen 6 measurements with a very well constrained redshift. Now, often oxygen 6 is accompanied by Lyman alpha. So if you have both Lyman alpha and oxygen 6, you know how much thermal or non-thermal broadening you have. But recently, some of the oxygen 6 has been detected without any Lyman alpha, and they have an unusually high line broadening, which is more consistent with a hot CGM than a one-hot CGM. So we just look for the oxygen 7 absorption at exactly the same redshift. We just need the quasar to be extra bright, which is one of the main challenges in X-ray. And here, as you can see, in both cases, we have a detection exactly at the same redshift at the oxygen 6 detection. And X-ray absorption is always going to be complementary to X-ray emission because one, it doesn't have the density temperature bias. So it allows you to probe the whole density temperature parameter space, while in emission, you will always probe a subsection only where one density is higher. And secondly, the metal tracers have higher emissivity. So we are always going to probe a subsection of density temperature in redshift. And also in absorption, we are always more sensitive to higher redshift simply because the flux will fall down very easily at higher redshift. So in X-ray emission, that's going to be challenging. But if the X-ray bright quasar is really bright, it is much easier to probe something at a relatively higher redshift in X-ray absorption. So here, same as the X-ray emission, we find that the implied mass is really large. And also in both cases, the impact parameter is at more than 100 kiloparsec. So here we do not have that mixing of galactic foreground. So we have an unambiguous detection from X-ray absorption that even at an impact parameter of more than 100 kiloparsec, we have hot gas with large column density implying a large mass. So with that, I will leave you with the summary in case of Milky Way. Initially, in the first 20 years, we thought we understood things. And now that we are looking further, we realize that we understand things less. There are complicated thermal, kinematic, and chemical anomalies that we have to understand. And if it is happening in Milky Way, it is not impossible to see this in external galaxies. But for external galaxies, right now we are mostly, constrained with a few detection that we have to first build the sample size up. And once we are more confident with those detections, we will try to see similar things as we are seeing in Milky Way. to really understand how the galactic feedback impacts the Earth's CGM. So with that, I will leave you with summary and take questions. Thank you for listening.
Great. We have questions.
Right. So, very interesting. For the Milky Way, when you talk that you are detecting stadium in Milky Way, where is that gas sitting? Is it like 10 kiloparsec? It will be showing the theoretical about which has a size of around 10 kiloparsec or so, or is it 100 kiloparsec? Milky Way has like a very right? So where is that gas sitting that you measure?
So in case of X-ray emission, if we just talk about X-ray emission, the scale radius is around 30 kiloparsec. So that's mostly closer to the galaxy. Like scale height will be 30-ish kiloparsec. But if we combine the X-ray emission and absorption, then the path length becomes more than 100 kiloparsec. So the X-ray emission is probing much lower density extended gas that's at a larger distance.
I'm just curious to hear a little bit more about observations, particularly about absorption. Were these proposals to observe quasars, or was it like were you looking at observations in the archive at a number of different quasars, or what?
Literally everything in this talk is archival data.
Right.
Everything. So all of the absorption measurements they were observed to study the AGN itself, not any intervening medium. And yeah.
So are there? I mean, I imagine there's a large number of quasars with observations, but maybe it's not so large. What are the constraints that you have to meet in order to have the observation be useful to you? Like gratings or flux level?
So for absorptions, we obviously need gratings. It has to be very high resolution. And also we need, so if we are talking just about the virial phase, for external galaxies, we need coverage in soft X-ray. So it has to be, for example, here, the wavelength is around 25, 26 angstrom. So we need coverage in grating in soft X-ray, and also very large effective area, because I remember doing a simulation that shows 800 kilosecond of XMM is equivalent to almost 45 kilosecond of New Athena. So it has to have a significantly larger effective area. And I do not really expect to resolve the shape of these lines given the very low column densities. So I don't think we don't need to significantly increase the R value as such. So high effective area is probably good enough for this. Yeah. I think yes.
Thanks, that was great. So you thought a lot about other probes of the hot gas, and well, first tell me if you agree, but it seems like there's a tension between what we're saying with KSD and weak lensing and sigma A stuff, and now fast radio bursts, which imply strong feedback with depleted halos. So is it just that AGN feedback is strong, and so the massive halos are depleted, whereas the Milky Way like galaxies still have a massive hot CGM, or what's going on?
Yeah, I think you have kind of answered it already in your question. So the thing is, in case of SG, so in case of FRB, you don't have any control of what intervening system there is. But in case of KSZ, almost all of the studies are focused on locally brightest galaxies, which by construction chooses galaxies with individual detection of AGN. So if a galaxy individually has AGN, you naturally have AGN outplan feedback. And if you stack 1,000 galaxies, you will just kind of amplify the effect of AGN feedback. But those are very small number of galaxies. I mean, they don't really represent the whole galaxy population, even at the same halo mass. So if you look at the galaxies at the same halo mass, but that are not like hosting an AGN individually, they might still have fast cycles of AGN feedback because these are relatively lower redshift galaxies in. But we have SD studies where we selectively focus on non-Asian galaxies, and there we do not see effect of strong feedback. So it is just a selection effect in SD that is giving, depleted CGM versus non-depleted CGM picture.
Okay, two questions. Yeah. So now that you have this figure up here, so particularly about these two galaxies, what are their average star formation rates? Are they actively star forming? Are they relatively quiet?
Both of them are actively star forming roughly at the same rate of Milky Way.
You know, number?
I think in this one, I think it was 3.5 solar mass per year or something. The other one I don't exactly remember, but they are Milky Way like. But the masses are slightly different. The first one actually is a Milky Way like galaxy. The second one is slightly more massive. It might be more like Andromeda in terms of stellar mass.
Yeah, the other question is early on in your figure, this is sort of a follow-up Akko's question about where the different phases are. I thought you had the supervirial phase inside the virial phase in one of the little sketches in the corner.
Yeah, that's okay. Yeah, let me go back to that. That's in emission. This one, yes.
Yeah. Is that the old style, new style? What is that?
Okay, so observationally, we do not have constraint on where the supervirial and virial phases are, if one is closer than the other, or if they're co-spatial. But given that supervirial phase always has a lower emission measure than the virial phase, if we try to fit their emission measure together with some density profile, this is the consistent picture. So it's more like model dependent scenario. But I'll just clarify, this is only the supervirial gas in emission. In absorption, we do not really know. That has to have a really large volume.
Okay, thank you, super. Thank you.
All right. I don't see any further questions. Thank you so much. Thanks. As a quick announcement, we do not have